Good morning, everyone. Jim Chastain, EasyPower weekly refresher session. This is going to be on smart design, specifically where to use it, what to use it on, and how to use it. First of all, we're actually going to start with a carryover question from last week where we were looking at hybrid flash calculations for both AC and DC systems. And the question came up about how to handle batteries and deal with wherever that places us as far as energy calculations. So we'll do that example first. Then we'll jump into the specifics on Smart Design. Smart Design is one of the most popular modules. It's an optional module that EasyPower has available. It's unique because it optimizes the leverage that we have in the Windows environment from the Windows file format, but it's a great example of how you can actually make your time more productive and more valuable by utilizing EasyPower tools. So we're breaking up into two parts. Today we're going to do setup and where Smart Design can be used, and then next week we'll be talking more about specifically how to Smart Design for your applications and needs, and how to take advantage of some of its transparency in the way that it manipulates the files. Smart Design is a rule-based sizing tool which uses tables of predefined components that we call design sheets. Most of these rules are primarily based on NEC, although they can be manipulated to utilize specific custom settings or to size the tools based upon other parameters in the system that may hold precedence for your particular project. The tools can size buses, cables, protective devices, and transformers. It only applies to low voltage systems, and it will essentially tell you no way, Jose, when it comes to the high voltage stuff. To be able to utilize effectively a Smart Design module, you need to have a one-line diagram that has at least one source, and the loads or equipment bus ratings have been defined. In the setup, you will define a specific cable length that's used in the calculations, and we'll go through a technique where these can be highlighted later on and realize where this optional sizing tool has done its work. Transformer step voltages or high side and low side voltages need to be designated so that the tool knows what translation of the source energy needs to take place. And you can actually invoke Smart Design per each circuit in a panel, per each load, or for the entire panel or an MCC suite set, and can be invoked as a subsystem or on a complete system, depending upon what you're trying to do. Elements can be excluded. You can size lock the parameters as you put them into the data block for that element and prevent Smart Design from changing those. So let's jump out of that straight into our EasyPower example for DC arc flash using batteries. All right, specifically we're going to use the example in the samples file called DC bus example 1. And if you recall, this is what we used for our arc flash analysis last week. Here we have the AC system, a step-down transformer from 13.8 to 208. We have a DC system with a rectifier that supplies a 250 volt bus with the requisite loads and protective devices. So we're going to go ahead and do a short circuit focus, calculate the branch currents, and then the incident energy. So the question comes up, well, what if we wanted to include batteries in this? Go back to database edit, and we're going to include a battery system now on our DC side. And again, it has the ability to be charged from the rectifier when there's available excess energy. We want to hook up the battery with a DC cable take pains to hook it to the positive side of the battery, and the tool realigns things to look as it should. Let's start with the battery definition. Again, I'm not a battery expert, so I'm going to be winging some of these parameters, and kind of bear with me because I think there's benefits from kind of even taking this approach. So the total rated voltage is going to be 250 volts. The total resistance, let's say, is 1.3 ohms, and the rated amps in this case, we're setting up for 1,000 amps. If I look at my system, I've only got two large loads over here, so this may be overkill, but we'll figure that out later on. I was going to say, since we're using SmartDesign, I might want to invoke it here, but let's go ahead and define the length of this cable. Let's say we have a 20-foot cable from our battery compartment. The one-way length resistance is calculated at 75 degrees C. We see that our maximum current rating is 310 amps. Since we're setting up a 1,000 amp battery, let's go ahead and make this a 3-conductor connection, and that'll get us at least close to the 1,000 amps, assuming that we're intentionally trying not to run at 1,000 amps. Again, this is not a recommended way to design a system, but let's assume this is the way it has been set up and we're inheriting it. Go to short circuit focus, fault the current, and so we can see incident energy in here. I don't see any numbers on this bus. I see that this bus is a little bit weird, and we're not going to pay attention to that now. And I've got reasonable energy levels over on this side. Oh, so I didn't include a breaker. Let's go back and include my breaker for the battery. Sorry about that. So I want to pick out a DC breaker. We're going to make it generic. And again, we have a 1,000 amp system, so let's set it up for 800 amps because we don't expect to be able to use all 1,000 amps for now. And if we set this up for 800 amps, let's say 700, it'll trip at 2,100 amps. Okay. All right, as we do this, we can see now that we have area of concern, and ironically, it's when we included this particular breaker. So if I open the breaker, I see that this bus comes back into a normal area, and this bus goes outside the range that's considered, or at least let's say the targets that I want to be able to work on the energized bus without higher levels of PPE. So the question is, what's going on here? And that's the place where the tools start to really pay off. So for starters, let's go in and look at my Arc Flash spreadsheet, and I'm specifically concerned about switchboard DC, and I can see here that there's no valid trip found upstream in the bus dialog. It's like, that's weird. I'm not getting any numbers here. And when I open up my battery breaker, I get excessive numbers. So if I come back down here and look now, I see that the protective unit in play is RTF1, which means that the rectifier protection now is taking place. So the question is, where is this particular breaker? Why isn't this playing into my protection scheme? All right, I'm still in short circuit focus. Let's go back and kind of look at all these variables. I'm still in short circuit focus. I'm going to expand this picture of the window out. And what I want to look at my options. So the way this has been set up for Arc Flash, this particular file, I can see right off the bat that we're excluding the main breaker, which is the reason this BL1 doesn't come into any of the calculations for this particular bus. We can also see that the engineer that set this up, or the person that set this up, limited all calculations to 2 seconds at less than 250 volts. Well, while there's certainly reasons to do that, it doesn't necessarily help me try to debug what's going on in my system. Let's go back and look at my fault bus. incident energy, arc flash spreadsheet. What I can see here is here's a case where switchgear AC 208 volt bus, the fuse 1 is a protective device, and the arcing time is set at 2 seconds even though the trip time is actually 8 seconds. So this is the reason that the 2-second limit was placed there, so that we don't get excessive energies on a low voltage bus. But even with this, we're getting excessive incident energy calculations, so this 2-second limit isn't really doing us any good. The reason I point that out, for just operating on it, if I go back and look at my short circuit options, my preference as I'm starting to look at the system is let's remove this limit, raise it up to 100 seconds so we can see what actually happens. Let's go ahead and change our breaker to include the main breaker and apply it, because looking at this bus I can see that this breaker will protect me from voltages upstream. And so now as we fault our buses and look at incident energy, we actually get reasonable results on all of our DC side. And I've still got my breaker open. With the breaker closed, which means the battery's in the circuit, now I've got excessive voltage or excessive energy on 3 buses, and so it begs the question, okay, was this the wrong breaker to choose, which it may be, and that might be the easiest fix, or are these incorrectly set? And the reason I ask that question is that as I go in and look at my power flow, the individual currents, I can see that I have 82 amps in this leg, 42 amps in this leg, and 35 in this leg, for a total of 200 amps. And this particular breaker, if I go back and look at it, this particular breaker is a 400 amp, set for 400 amps or 2400 amp trip. So my choices are, do I modify the protective devices here, or do I modify it at the battery breaker? One way to look at this is going to look at the coordination focus. Let's highlight this particular set of cables and load and plot the TC curves. And so what we see here, as we compare BL2, BL5, and the various bus faults, I'm going to fault this particular bus, and because we're looking at BL5, let's see where it went. It's BL2, BL5 is the blue one. If I insert the arcing fault, I can see that the arcing fault current for BL5 on this particular bus is literally in the place where the settings on this particular breaker that will cause the longest trip time at this calculated current. And what that means to me is I need to reduce the settings on the breaker, and watch what happens over here. If I show my incident energy, I go back and put the breaker what was, we have a high level of incident energy with this arcing current. If I reduce the setting on the breaker just a little bit so that the arcing current now falls into the instantaneous area of the trip settings, I get a reasonable instant energy even with the settings I had before. All right, let's go back and do the same thing now with the bus above this. We're going to fault this bus, in which case now this breaker's in play, the purple one, that show our arcing current. We have exactly the same problem here where our arcing current is in the most disadvantaged place as far as calculating what the incident energy is. If we reset this bus, this breaker just so slightly, or if it can be set, So I guess what I see is this breaker, which is BL2, is actually set too high for the type of loads that we're carrying. And as such, if I open up the temporary settings and say, rather than 400 amps, because we're only carrying a couple hundred amps on this particular breaker, if we take this down to a setting that's more in line, now it looks like we have a better incident energy, because now this trip setting is going to fall in a more civilized part of the curve, which also leads me to believe maybe we ought to relook at what's going on with this breaker, because instead of 400 amps, well, we may not have another choice. All right. The point that I'm trying to make is at this particular setup, it looks like we have miscoordinated breakers, and yet, because the trip currents are offset by enough that this breaker will protect the trips and isolate this motor, and this breaker will trip a little bit less but could simultaneously trip, means we might have coordination problems. But when we go back to the overall system now and fault the buses, you can see that we have incident energies that reflect the protective device. Let's look at our short circuit, fault the buses, incident energy, arc flash. All right, so the only place that's out of whack is switchboard DC. And again, we learned earlier that that was a result of putting the battery in play. And so rather than, I guess, if this were my plant and we had made the discussion at this point that we followed, there would be a procedure before I had to work on this bus of taking the battery offline, and consequently would be part of the hard work permit in working on this bus. You notice that the energy is there whether or not the rectifier is online. It also shows, this also shows that the breaker for the battery is set too high, because it actually increases the energy downstream if we're powered on the battery. So I guess what this points to is the value of the tools to analyze all the different scenarios that we're exposed to when we have to deal with batteries and multiple sources in a system. Not necessarily the way to design a DC distribution system. Okay, jumping into SmartDesign. Hope that helped with the questions on the batteries. Again, this particular example is in the example folder, and what it does is shows us the application for SmartDesign, and we start by looking at the fact that none of the cables are sized, none of the transformers are sized, none of the breakers are sized. We have defined the voltages. For instance, this is a step-down transformer from 13.8 to 480, and we have done a very specific detail of all the loads inside of, in this case, the MCC panels, where each of the motors and all the parameters from the manufacturer's data sheet have been listed. But we've not, other than designate that it's a multi-case circuit breaker, we've not done anything with the sizing of the breakers, or as is included in the rest of the MCC spreadsheet, the sizing or the length on the conductors or the neutral or the conduit. Likewise on panels, we have all the connective load, the phases, but nothing set up for protective devices. Okay, so what determines how this capabilities of the Autodesign are invoked is the options list on Auto Design option. We can get to it from a pull down for auto design, or we can get to it from the options list auto design. In either case, it brings us to the options dialog box for auto design settings. First of all, we have the ability to select a generic library sheet, which is the list of all the parts that we're going to allow the tool to draw from. We can have multiple versions, multiple renditions of the generic. Also built in with the tool are several catalogs from a couple different dates of leading suppliers in the industry: Square D, Siemens, GE, and Cutler Hammer. And again, these are dated. So let's start with just generic to begin. We can generate a report only without changing any of the data. Consequently, the one-line diagram won't change. We can create a report with or without the bill of materials. So in this case, we're going to be creating the report and we're going to be changing the one-line diagram. The downstream load is based upon, in this case, the code. If for some reason we want to say, nope, base the sizing on what I have connected, I don't care what the code says, or on a specific current level because I haven't decided what loads I'm going to take, these are all can be set up and controlled from this point, from this setup sheet. Likewise, sizing MCC panels on the one line, we size the bus, the main, and the feeders, or we can size everything. And if we size the bus, the main, and the feeders, we're not sizing the breakers. So we're going to size everything. If there's a motor in the circuit, we tell the, at least the calculation engine here, to use full voltage non-reversing, a typical full voltage starter. If we're doing a specific circuit or a sub-circuit where we have specialized starters, we can designate those at this point. Where there's a line, when you're choosing a cable, we're telling it which type of cable to use. And in this case, I use 99 feet as my default length because that way I can go back and look at the one-line diagram. Any place there's a 99-foot indication, that means this tool did the insertion of the data, and consequently I need to go back and update that whenever we have the as-built or we're closer to the physical dimensions that the installation is going to actually have. And then we can size based upon the tap or plug rating or on an adjusted value. When we're picking max protective devices, select based upon the maximum or minimum available pickup settings and size the feeder breakers either on the bus rating or on the load. If there's a if there's a motor in the circuit, use these parameters for locked rotor multipliers, and as we're calculating what the voltage drop is downstream at that load, if the voltage drops more than 5%, then upsize the conductor by 20%. Now, these are variable numbers. We can make this 12 and upsize by 30 if we want. We can make this 6 and upsize by 25. Again, this is based upon our anticipation of changes in the system downstream and maybe oversizing the cable so that we don't have issues, especially if there's going to be long runs or additions later on. So this is, again, customizable. And then finally, we can allow sizing to the bus or not. And so in this case, we're going to allow sizing. By applying now these rules, we can go in, and if we're looking at an MCC circuit, we can pick out a specific pump, a specific bucket, right-click, auto-size a protective device and cable. As we do that, it tells us that it was successfully sized, and it will be detailed in the report. So as we look at the circuit for the MCC, we see nothing's changed on the motor specifications, but sure enough, it's picked out a molded case circuit breaker from the generic file, standard type, an MCP 150 AF, trip setting of 30 amps with an interrupt rating of 65, full voltage non-reversing, starter size 0, 1X, insulation. These are default values for our cables as we draw on them. Conductor size is 12 based upon the load. Again, we told it to use 99 feet, but this could be anything. The conduit size now is spelled out. The ground size and the material is being used. Now, as we go in and look at our, under the Windows stack, we'll see an auto design report. And so now this tells us, specifically for that MCC circuit that we selected, here's the cable sizing and the reasons that it was done that way. Here's the breaker sizing and the reasons that it was done as we requested. And so this is where you literally justify the selection of the parts based upon chapter and verse of the NEC. Now, just as we indicated, if we wanted to apply SmartDesign to just the whole panel, we're going to go in, select the panel, and then auto design. And as the panel changes color, we go back and look at description. And just as well, we go over and look at the protective devices. Again, we have all standard breakers. In this case, they're all the same size with different trip settings, same family, so the same interrupt rating, and again, all 99 feet. If we look at the left side, we get this similar result. And again, the auto design report will give us essentially warnings when it wasn't able to accomplish what we asked or whether it doesn't make sense. In this case, the cable rating is 10 amps, which is smaller than the panel rating at 100 amps. And so we really need a designer to look at this, just have human eyes look at this to see that it makes sense for the project. Now, because there are prices included with the selection in the generic part design sheet that we selected, we can come up with a bill of materials report. And because we were just doing a specific panel, this is what the cost of the elements that we had selected from the catalog, the generic design sheet, to do that population of this panel. Now, if we want to go back and say, well, that's all well and good, but I really want to see what would happen if I used Square D, say the 2007 catalog, and instead of my 99 feet, I want to use 55 feet with the same logic, and I apply it. And this time, instead of doing just a panel or an MCC circuit, let's do the whole subsystem. I invoke auto design. I selected the whole subsystem, invoked auto design, and as it kind of comes back to me, I can see now I have all Square D part numbers. The breakers are all sized for the specific load. The cable links, they're all set up for 55 feet, and they are sized. Here we have a 600 kcmil cable set up for 450 horsepower, 415 horsepower, and we only got a 1C2 AWG cable to supply this small panel. Transformers have all been sized, and the buswork has all been sized. More valuable, I think, again, than just the fact that we update the one-line diagram is that we give chapter and verse based upon what the tool is able to accomplish. Again, it doesn't work on high voltage, so the report's telling us that the designer needs to deal with this sizing. And as we go through the specific parts that were selected and what the parameters used to make those selections are, we can see specifically what those numbers are and do a hand calculation to make sure that we have the guard band we're looking for. But more importantly, now we can pay attention to the exceptions, so our time is spent more productively by eliminating the exceptions rather than dealing with all the tedium of going through the sizing on each element. And especially where there's a error reading, here we're showing that panel row 5 was not sized because everything was set to 0, and so this doesn't make sense, so I need a human to look at this. This report can be exported to Excel, to Word, or printed as is. And just as before, we also have a bill of materials report, and so now we can see, based upon selecting these components from a Square D 2007 catalog, albeit a little bit dated, that this particular project will cost approximately $27,800. I'll make that $278,000. That doesn't seem right, but that's what the number's coming up with. Oh, I think it's because I changed a price in there, which actually leads into the next week's discussion, and that is how to customize the library. Now, all this information comes from the device library, and the fact that one of the questions I get very frequently is, okay, how often do you update the prices? The answer is we don't. The 2007 price is what the 2007 price was. And that's the subject we'll be tackling next week. So we've used up our 30 minutes. Let's see if we got any questions either about the battery or about smart design. Appreciate everyone attending, and we'll be picking up the discussion next week and showing how to customize and tune smart design specifically to be more valuable for your applications. Thank you very much.